Good morning, ladies and gentlemen. Be welcome to this webinar, part of the International Solar Alliance Expert Training course. This webinar today is the introduction to Module 4, Technical Integration of Photovoltaics. I am Paul Arranz-Piera. This expert training series from the International Solar Alliance are prepared in collaboration with the Clean Energy Solutions Center, the Carbon Trust, the companies Aguasol and Trama Tecnoambiental. As I mentioned, this webinar covers the introduction to module number 4. Module 4 is focused on the technical integration of solar photovoltaics. It's part of one of the 8 modules of this expert training course. A few words about myself. I'm a project director and engineer at Aguasol, which is an international energy consulting and engineering company based in Barcelona. I have previously worked for Trama Tecnoambiental and the US Corporation, and I have over 20 years experience in the renewable sector, renewable energy sector, and energy efficiency. I'm also an associate researcher, a lecturer at the Technical University of Catalonia, UPC. Module 4 webinars also prepared by Professor Oriol Gomez Belmun. Dr. Belmun is a professor in the Electrical Power Department of UPC. He also sits on the board of a research group, CITSEA, where he leads a group of power systems with an interest in power electronics and renewable energy generation, mostly photovoltaics and wind, high voltage DC transmission systems, and power converter based systems, mostly focusing on energy storage and electromobility. Professor Gomez has over 20 years experience, and he's involved in a series and a number of research and academic projects, also collaborations with industry, a number of several journal publications, books, and also patents. So this webinar, as an introduction to Module 4, I'm going to cover very quickly. I'm going to do a quick revisiting of the basics of PV systems, PV plants, and I'll discuss levels of integration of PV systems, and I will spend most of the time describing or summarizing the different webinars that are part of module number 4, technical integration of PV systems. So some quick recapping on the solar photovoltaic technology, which allows the obtention generation of electricity from solar radiation, thanks to the photoelectric conversion, photoelectric effect that happens in the PV, in photovoltaic cells. Solar cells, as I'll describe in a minute, are rated under specific conditions known as standard test conditions, and probably the most significant of them being the level of solar radiation received, rated at 1000 watts per square meter. That is the incident solar irradiance level that we use to rate PV cells and PV modules. Some orders of magnitude, on the Earth, we are receiving continuously about 154 billion megawatts continuously from the sun. Tremendous amount of energy from the sun that we are trying to put into good use and generate electricity. Solar energy is very probably the best distributed energy, natural energy resource we have on Earth. And not only that, but also it is a resource that coincidentally is available in those areas where lowest access to electricity at the moment. So we have a good match here with the abundance of solar energy resources and lack of electricity access at the moment. From this point of view, the role of PV systems is essential to increase the universal access to electricity in the world. Some quick recap on the basic concepts of solar radiation. We have irradiance, that's a flux of energy measured in watts per square meter. Irradiation, which is the energy the radiance that's been captured or received by a surface over a certain period of time. And as I mentioned before, a nominal power capacity of a PV module, which is measured or defined under certain conditions known as the standard test conditions, or STC. Radiance of 1000 watt per square meter, temperature on the modules of 25 degrees Celsius, and an air mass of 1.5, which is a series of physical parameters that have to do with the distance between and the angle of incidence of the solar radiation onto the surface of the PV module. One of the key aspects of photovoltaics that are very important for the integration into buildings or into grids is their modularity. PV modules are constituted or are essentially composed of the connection of several PV cells that are connected in series to conform a module. Then in turn, modules are connected, different modules are connected to each other to form strings, and then several strings are connected to each other in parallel to conform arrays, PV arrays, or PV modules, or PV fields, which are the generation part of a PV plant. But PV plants or PV systems are more than just the PV modules. In a PV plant, we can recognize, we can see several functions. The generation is one I just mentioned, but we also have storage. We also have conversion of the electricity generated from the PV panels. Remember, that's electricity generated in DC, in direct current, that needs to be adapted to the consumption loads and alternating current, AC, or feeding into the grid, into grids. And then that will be the main functions in a PV plant, but also considering the control function of these different aspects, together with the monitoring, data collection, and information to be able to take decisions and to control to manage the performance of the PV plant. Then PV plants, of course, have to there has to be an interface between the plant and then the further use of the electricity that's being generated by the PV plant, whether it is a building, a house, or an industry, or the grid to which the electricity being generated by the PV system is being injected to. So, Module 4, as mentioned, deals with the integration of PV system. So from that goal, a direct question would be, so what is an integrated PV system? Well, one first reaction we have to that is that PV systems should be not just installations, but rather comprehensive projects, complete projects where two different kinds of integration is considered. First of all, the integration into the building level. Yeah, the systems will be built, will be sited in specific buildings or facilities where they have to be properly integrated into the operational aspects of such facility or such building. But also the social use, the use of that PV system into those particular buildings is of importance. And finally, the integration on the building envelope, the architectural integration of the PV system. And then after building or beyond buildings, we have the integration of those PV systems into the grid systems. Module number 4 is looking at the integration beyond buildings. Examples of integration into buildings, of course, there are multiple examples. Fortunately, in the year 2019, we have lots of buildings that are already containing PV systems. For instance, we have 3 examples here, one from Abu Dhabi, arid environment where we see PV modules installed on a roof of a learning center. Another example from Germany, PV systems, translucent PV systems that are nicely integrated into a facade of an office or a residential building, or headquarters of a company, commercial building in Barcelona, where we can see PV systems slightly inclined, also installed on a facade, but slightly tilted, integrated together with windows on a south-facing facade. Of course, the decision of having installed PV systems on facades is telling us that whoever that made that decision took into account in a way, it was an offset between or a trade-off, sorry, between losing a bit of efficiency of having vertically oriented vertically mounted PV systems. This is a loss of efficiency versus the visibility of putting PV systems in a facade. So those are examples of integration into buildings. Now, module number 4 is dealing with the integration aspects beyond buildings. So that is integration into grids and grid systems. So the relevant topics, different topics that are covered by module number 4 are listed here. We apart from this first webinar, introductory webinar, we have prepared 7 different webinars. The first one dealing on the technical integration of photovoltaic systems into distribution grids. Second one, the planning on distribution networks that is affected, or what aspects need to be considered in the planning of distribution networks when we want to integrate PV systems. Webinar number 3 is similar approach, but to transmission networks. What would be the challenges? What would be the strategies to achieve increased PV penetration into transmission networks? Webinar number 4 is about smart grids. Number 5 has to do with control curtailment options and how to activate such, how to manage and implement such control options using remote solutions. Then webinar number 6 about the role of inverters and advanced inverters to facilitate the integration of PV systems. And the last webinar in this module is focuses on the development of grid codes to facilitate the integration of PV systems. The integration of PV plants into current grids is heavily motivated by two paramount aspects. Number one is that power systems today are experiencing deep transformation. We have new actors participating in power systems. We have different and new technical approaches, technology innovation, the role of users, final users that can also become electricity or power producers, giving way to this concept of prosumers. And all of that largely driven by a global international concern or an international goal of increasing the generation of electricity from renewable sources. Of course, that has been motivated by climate change drivers and other situations of scarcity of fossil fuels, etc. So point number one, or aspect number one, is the changes, transformation on power systems. But at the same time, such potential change in the mix of generation is also raising a lot of concern by grid system operators. And as such, PV power plants, photovoltaic power plants, apart from generating power, they also need to be operated and regulated, observing conditions of reliability, of security, to support current and future power systems. So we have these two main drivers in the context of discussing the integration of photovoltaic systems into current grids. One first question that is discussed in the different webinars in this module is the flexibility of PV integration, and for that there's a number of strategies that can be followed. One of them being the modularity of power systems themselves that I mentioned in the introduction. Different strings, different ways of configuring PV arrays. So there's a number of possible topologies, different topologies, different PV power plants configurations that can suit whatever requirements from distribution grids or even transmission grids could be, and different arrangements on power on the inverters condition, including central topology, centrally driven inverters topologies, or string or multi-string inverters are possible. Then the different from the electrical power design configurations can be considered, considering or thinking of radial or ring or star systems are all of them valid possibilities that can be applicable to PV power plants to facilitate their connection onto existing grids. Depending on the large-scale penetration of PV power plants is typically designed at a medium voltage, but the connection at low voltage is also possible. Of course, the additional equipment is needed to facilitate and to enable such flexibility of power plant layout, transformers, switch gears, and in some cases, reactive power equipment and energy storage systems, batteries are also important to introduce flexibility in the layout of the configurations of PV power plants. In this slide, we can see different examples, different topologies of PV systems integrations, whether it is central inverter topology or string inverters topology, or even multi-string inverters topology. All of these are possible PV plant configurations that offer flexibility to designers, to engineers, to better adapt the generation potential or capabilities to the conditions of the grid. So all of these is just a snapshot of some of the ideas that are discussed in the webinars on PV plant topologies, and of course we invite you to listen or to watch the webinar that is specifically dealing with these descriptions that are part of the Module 4 series. Another webinar is focused on the impact of PV systems on distribution grids. Very quickly summarizing this webinar, we can say that PV power plants are essentially distributed generation points to be integrated in a distribution grid. Of course, conveniently installed or located, PV plants can contribute to reduce or to increase the loads of the specific distribution lines, so that can help balancing current unbalances of distribution lines. But of course, such PV plants will have an impact on the overall system voltage, and that needs to be studied and carefully addressed. Energy storage systems, for instance, imagine electric cars, charging stations, flexible loads can help in the integration of PV systems, and can be a useful strategy within distribution grids. In this slide, we can see an example of how distributed PV systems are considered in a given distribution grid. Several households with PV systems introduced here and there to balance the condition, the load of the given distribution grid. Another webinar is looking at the challenges of introducing PV systems into the transmission grids. Of course, in the world of transmission, from the point of view of the transmission grid, the variability or the seasonality of PV generation is of concern because of its sometimes limited predictability. That is, by comparison with conventional thermal or hydro power generation, this could be a drawback or a disadvantage, you know, of PV systems. Well, that is a condition of PV systems that needs to be taken into account from the transmission and integration point of view. Of course, the predictability of PV systems performance is key from that point of view. So the improvement of the algorithms that can predict that is of great importance to improve or to increase the introduction of the penetration of PV systems generation into transmission systems. Demand generation balancing issues like fluctuations in frequency, issues related to voltage and power flows, or how to offset the short-term additional costs that the penetration of PV systems generation into the transmission grid are aspects that are of concern and are described in more detail in one of the webinars of this module. Just as an example, in one of the webinars, the different stages of evolution of a large-scale PV integration impacts on the transmission system could be that is discussed in this webinar. From phase 1, where variable renewable energy generation is very little and has no impact or no noticeable impact on the system, all the way up to phase number 6, where there could be seasonal or interannual surpluses or deficits to this variable renewable energy supply that then have a great impact on the stability of the transmission system, and therefore has to be properly addressed and properly balanced. Another webinar in Module 4 discusses in detail the relationships or the possibilities, the role that solar PV systems have in smart grids. In that webinar, we will explain what the smart grids are and what are the advantages that PV systems offer for the ultimate goals of smart grids. Of course, smart grid is in the conception of the smart grid. There are a number of issues that are different to a conventional grid. Perhaps the most significant of them being the combination of energy flows, being electricity, heating or cooling, together with information flows with the data for a number of different consumption patterns, different users, and different generation points. In that sense, it is obvious that the way we design and we build PV systems is essential to facilitate their integration into grids, and not only grids, but also grids that we want them to be smart or smarter than they are now. From that point of view, the components that we need to find in a PV system have to facilitate not only the flow of power, but also flow of data and communication. And for that, there's a very key component of PV systems, which is the inverter, that will have to primarily deal with these two elements. There's a specific webinar that is focused on the role of inverters, which I'll comment in a few minutes. Of course, the type of inverter that is considered in a PV system will have different results, different consequences on the possibilities of enabling a smart grid, and but also the use of one type of inverter or another will also have implications of costs. In this slide and in this webinar, we will offer more details on the issue of inverter costs. Smart grids and photovoltaics is quite a big topic in itself, where we can distinguish several focus areas that give way to several industrial subsectors or sectors of industrial interest. Just to name a few: the distributed energy system sector, the transmission distribution grid management sector, different strategies, different solutions, different equipment related to grid monitoring, control, security. Also, another industry area is that area that is looking at how to increase the matching between consumption and generation, facilitating a wider range of consumer choices and enabling different business possibilities and markets. The software industry, specific software, advanced software and hardware that's directed to facilitate solar energy generation and smart grids, from energy dashboards, controllers, the world of sensors, even the Internet of Things, smart appliances, etc. And also, finally, communication systems, smart meters that are should be able not only to measure energy flows, but also to collect, measure data and consumption data, and be able to transmit it real time to facilitate the decision making. Yeah? There's a number of aspects in that sense that are discussed in the webinar that you will find as part of the module number 4. If you're interested in the possibilities of photovoltaics with smart grids, I invite you to check that webinar. Another section as part of this module deals with the importance of control systems and communications. Yeah? Power plant communication systems need to facilitate the system operators the reception of information on the power plant state and the different set points that are necessary to optimize the matching of the PV generation and the grid conditions in terms of active power, but also reactive power exchange. A typical example of that, which is analyzed in this webinar, is a command of active power curtailment, essentially meant to avoid congestions in the power system. Of course, communication channels, adequate channels, and probably adapted channels will need to be developed to enable the adjustment of such operational set points from PV power generation plants to suit the grid code requirements, different grids that to which this PV generation is injected. In the end, power plant controllers of PV generation facilities will be the responsible to coordinate required actions at the same facility for the sake of the proper balancing and stability of the grid. So we have a specific webinar in this module that analyzes the strategies and the examples of communications and control systems specifically tailored at the integration of PV systems into distribution or transmission grids. Another of the webinars in this module is, as I mentioned before, is focus centered on the role of the inverters. Inverters, we can consider them as the true brains of the PV system integration, the essential element or the key component that will facilitate such integration. Solar inverters are doing many things. Perhaps the first and foremost feature that inverters have is the conversion of DC direct current output of the PV cells, PV panels, into the AC alternate current, which is injected to the grid or directed to the loads. In case of standalone configuration, or a mixed configuration, or self-consumption configuration. So apart from the DC-AC conversion and the voltage adaptation to the grid conditions, solar inverters are also maximizing, or responsible to maximize the PV generation of the features of MPPT, maximum power point tracking. They also need to be vigilant to protect in case of islanding. They also need to be caring about the synchronization with the grid, and well, in general terms, to support the grid where the PV system is connected. So inverters really need to be carefully chosen, carefully assessed, because their conditions, their performance will heavily will have great consequences on the performance of the PV system and its level of its effective level of its integration into the grid, where the PV system wants to be coupled to. And finally, the last webinar on Module 4 is focused on the role of the grid codes and what requirements need to be taken into account to facilitate the integration of PV systems into the grids. In the end, these codes, grid codes, are the requirements that will be imposed by the power system operators, in the sense that a power plant, in this case a PV, solar PV generation power plant, must accomplish in order to be connected and to sell energy to a particular grid. These requirements that, of course, will be driven by the optimized integration of such solar generation in terms of stability, in terms of security, etc. All these requirements will need to be detailed in a series of documents known as the codes, or the grid codes, that will define in detail what is the behavior expected or required to such power plant, both in steady state conditions, but also during the transient operation of the plant. For instance, as an example, in Spain, the connection of wind power plants is defined by operational procedure documents PO 12.2 and PO 12.3. Finally, just to go through the list of items that is covered in each of the webinars of this module. First webinar, technical integration of PV into distribution grids. Well, in that webinar, you will find discussions in terms of topologies, PV power plants, considerations on the panel, string, or central inverters, analysis of plants, power plants, PV power plants layout, and some other analysis requirements for the auxiliary equipment, and also the integration of energy storage and its impact onto distribution grids. In terms of planning of a distribution network, there's another webinar addressing the specific issues of planning, considering the role of PV plants as distributed energy sources, what would be the impacts of PV plants and distribution grids on line loading, on system voltages, the consideration of storage, flexible loads integration, and discussion of several examples. The following webinar is dealing with planning of transmission networks and the integration of photovoltaic and other variable renewable energy sources. In this webinar, the challenges for the transmission systems and their operation are discussed. The key impacts of PV systems penetration in the planning of these networks is discussed in this webinar. Impacts in terms of flexibility, on curtailed energy, impacts on the reserves that need to be granted to be present in the transmission networks. Then also the impact in terms of cost of PV integration in the transmission networks and the uncertainty that at the moment is there, which is a case for further analysis, more detailed analysis, as more PV systems are introduced into transmission grids. And then some case studies, discussion and examples. Another webinar, smart grids and the role of photovoltaics into smart grids. This webinar deals with several issues that are listed here. Why do we need smart grids? How can we define smart grids? What is the difference between smart grid and the traditional grid? Focus areas, technologies, components, the different designs that are specifically aiming for the integration of PV systems into smart grids, the advantages, barriers, costs and benefits of PV systems integration into smart grids, and again some case studies. Following the next webinar on remote controlled curtailment options for solar PV system integration, deals with what are the current approaches of remote control, PV power plants, the structure of power plants controllers, controllers that are specifically dealing with reactive power, controllers dealing with active power, and some examples of each one. Following the next webinar, Advanced Inverters for PV System Integration. This webinar deals with the basics of converters, fundamentals of electricity circuits, functionalities of solar inverters, characteristics of inverters in terms of current voltage and power voltage characteristics, capabilities of maximum power point tracking, principles of control in inverters, single stage, two-stage inverters, and the features of galvanic isolation or anti-islanding detection. The next webinar, grid code development for PV system integration, deals with start by offering a context of the electrical power system and how codes are prepared and what they aim for. In the grid code development, the conception or the approach, different evolutionary states of photovoltaics, from PV farms to photovoltaic power plants, specific aspects of concern in grid codes development, such as the voltage support, frequency support, the inertia emulation, black start, ramp control. All of these elements, all of these aspects are discussed in detail in this webinar on grid code development. So thank you very much for your attention. We've come to the end of this introduction webinar to module number 4. So we invite you to watch the different webinars, 7 webinars that are part of this module. And we hope you have enjoyed today's webinar, and we look for your participation into the solar expert training courses as part of this module. Thank you very much.